A histogram can be defined as a representation of frequency distribution by means of rectangles whose widths represent class intervals and whose areas are proportional to the corresponding frequency. So this is a definition by the Merriam-Webster dictionary. What we mean by that is that, for example, when we look to the sine wave, so we have values from -1 to 1. We will divide these values in some intervals that we are going to call bins, and then we will count how many values are inside each bin, and this way we can build a histogram. Here I'm just defining some distributions and SymPy that we're going to use later on for the PDF. We're not going to use now, but I'm just importing the SymPy symbols function, and from SymPy statistics we're importing a uniform and Laplace. And it's very important to observe that a histogram becomes a probability distribution if we divide it by the total number of samples, such that its sum becomes 1. So this is how it looks like a histogram. So what we're doing here, we're plotting all these 4 histograms. So we're calculating here, we're using matplotlib to have the histogram, and we're using here the sine wave, the noise from a uniform distribution, the noise from a Laplace distribution, and the musical signal. And we have here this density equals true. That means that we are dividing it by the total number of samples. So this is why we have here, for example, this is the uniform distribution signal, and its values go from -1 to 1, and we see here that the average here is 0.5. So here we have the sine wave histogram, here we have the Laplace distribution signal, and here we have the music signal. So all these histograms, they are normalized, so they are divided by the total number of samples. Yeah. So for example, if I replace here, and we have density equals to false, so we see now the sine wave is 1.4, but it goes to more or less 9. It means that there were like 9 values inside this interval from -1 to the width of this bin. So I'm using here 20 bins, so I'm dividing this range from -1 to 1, 20, so it is approximately here from -1 to 0.9, 0.8, 0.7, 0. And so on. So from 0.1 intervals we have here. Now let's go back to the density true, because we're going to use this property of histograms, normalized histograms and probability distribution later on.